Hello, welcome back everyone. Today we'll be getting into section 4.3. Time permitting, we'll go back to 4.1 and 4.2. Those are mainly reviews of things that already happened earlier in the book. And 4.3 is something that we have not done in the book. So if we have time later in the semester, we'll go back. But we lost a week with the pandemic and such. So right now we'll be getting into 4.3 on quadratic equations. So we'll start with just a quick little mini review of a quadratic equation that you already could have solved back in your Math95 days. This one we will solve by factoring. So x squared minus 8x is worth negative 12. So hopefully you remember from your Math95 days, what's making this quadratic is that we have an x to the second power and no higher powers, no variables underneath radicals or at the bottom of fractions. For solving it by factoring, the idea is we want to set one side to 0 first. So in this one, we would simply add 12 to both sides. So x squared minus 8x plus 12 is worth 0. And then we're looking to factor this thing. So a is 1, b is negative 8, c is worth 12. So a times c, we're looking for a product equal to positive 12 with the sum of negative 8. Multiplying to a positive, so we know we have two of the same signs. Adding to a negative, so we know everybody's got a negative. So negative 2 and negative 6 have all the properties that we need. Since we have a leading coefficient of 1, we can do the fast factoring. So x minus 2 by x minus 6 is equal to 0. Multiplication problem ending in 0, one of those two factors had to be worth 0. So either x minus 2 equals 0, union that up with x minus 6 equals 0. And then we're just solving the linear equation in one variable. So x plus 0 turns into x, 0 plus 2 turns into 2. Union that up with adding 6 to both sides of the other one. X plus 0 turns into x, 0 plus 6 turns into 6. Those are both in the set of real numbers, so we will keep them. So now our domain is not just I, but R. Since these are in the natural numbers and the whole numbers and the integers and the rational numbers and the real numbers, we get to keep them. Now, the nice thing about the factoring method that you learned back in 95 is fairly straightforward, not too terribly difficult. The thing that isn't as nice about it is it doesn't always work. In fact, with real drawn from data quadratic equations, it's rare to find one that's factorable. So we do need other methods. So those other methods are going to involve square roots. So just a little mini review on the ideas behind square roots. When we use the radical symbol, we're looking for the principal root. So even though I can do negative 3 times negative 3 to reach positive 9, with this radical symbol, I'm only looking for the principal one, the positive 3. Square root of negative 9. I'm looking for two numbers that I multiply them, two copies of the same number to multiply to get a negative 9. Well, two negatives make a positive. Two positives multiply together get a positive. And 0 times itself is always 0. So this one we would say is not an element of our set of real numbers. Where I place that matters, though. Outside of here, this is just asking for the opposite of square root of 9, which would be a negative 3. So where that is does matter. Underneath it, you're looking to multiply two copies of the same thing together to get a negative. It's not possible. If I try -3 times -3, I get a +9. +3 times +3 is also a +9. Outside, we just want the opposite of that original square root of 9. So one method that can be used on these quadratics is what's referred to as the square root method. So the basic idea here is that we get it to where we have the form of expression squared equals a constant. This is the scenario where we could use the square root method. So this first one we'll need to do a little bit of work to get it there. If I wanted to factor this thing, I would be out of luck. I would be trying to multiply to -5 and adding to 0 using two integers. Multiplying to -5 using integers, my only options are -1, +5, or +1, -5. I won't be able to get to that 0 using integers. So I'll make it look like this. Perfect square equals constant by just adding 5 to both sides. X squared plus 0 turns into x squared. 0 plus 5 turns into 5. Once we have perfect square equals constant, we use the square root. But because we want both roots, not just the principal root, we have to introduce the plus or minus on this stage. Highlight it, draw arrows by it, write it in bright red ink, something to remind yourself that you need that as soon as you've introduced a square root to a problem that didn't have it before. So left side, then we have square root of x squared. Those are inverse operations. That'll give me an x, plus or minus square root of 5. Now, if we were talking about an integer domain problem, we would go to saying that's the empty set since these are irrational. But if we're in chapter 4, we're talking now a real number domain, so I get to keep both of those. Opposite of square root of 5 is one of my answers, square root of 5 is my other one, and both of those will go in my solution set. So our next one, x squared plus 16 is 0. Same idea. I'll try to get a perfect square equals a constant. X squared plus 0 turns into x squared. 0 minus 16 is -16. Square root of both sides, plus or minus on the side with the constant. Now, as soon as I see this, square root of a negative number, that kicks us out of the real numbers. So my solution set is empty. So this is outside of the real numbers. So if you think back to our Euler diagrams of the real number system, real numbers, we had our irrationals and our rationals. Within the rationals, we had our integers. Within the integers, the whole numbers. Within the whole numbers, the natural numbers. We had been working here. Starting in chapter 4, we expanded it all the way here. Square root of a negative brings us outside of that. So we could add one more layer to our Euler diagram. This would be in our complex system. So all of the reals are inside of there. Square root of -16 or negative square root of -16 are both in the complex but outside of the reals. So there are no real numbers that will get that job done. So those are still outside of our domain. Now, occasionally they'll give us some problems that we have a little bit of more work to do, but still rely on the same method. X minus 7 squared is worth 5. We still have the setup of something squared equals a constant. We can use the square root method on this. So square root of x minus 7 quantity squared is equal to, don't forget your plus or minus. It has to be there even on that first step where you introduce the square root. Plus or minus square root of 5. Left side, the square root and the square are inverse operations, so we're left with our x minus 7. So x minus 7 is plus or minus square root of 5. And even though this is really two equations, I can solve it as if it's temporarily just one equation. I'll add 7 to both sides. X plus 0 turns into x, so x is 7 plus or minus the square root of 5. 5's not a nice, neat, pretty, perfect square, so that's as far as I can go simplifying that. So we have two numbers in our solution set, 7 minus the square root of 5 and 7 plus the square root of 5. Plug either one of those into the original, and you'll see you do get a true statement out of the original. Okay, one more using the square root method, then we'll go on to our last method for these quadratics. X minus 2 quantity squared plus 6 is worth 8. This one, I don't have the right format yet. I want perfect square equals constant. I have perfect square plus some extra stuff equals constant. I need to fix that. So I'm going to subtract 6 on both sides. So x minus 2 quantity squared is worth 2. Now we have the right setup. Perfect square equals constant. Now we can use that square root method. So I'll take the square root of the left side. I'll do the plus or minus thing in front of my side with the constant. So x minus 2 is plus or minus square root of 2. 2 is not a nice, neat, pretty, perfect square, so we'll just leave that under the square root. So x is 2 plus or minus square root of 2. Those are both in the set of real numbers, so we'll keep them both in our solution set. Now, if we don't start off with something that's factorable, or a nice, neat, pretty, perfect square equals constant format, we do have one other option to us, and that is the quadratic formula. Now, if you had taken Math 100 instead, you would derive this and see how it's made. This one, the author is just saying, take our word for it, this is how it works. I would suggest, though, since you're expected on the quiz, test, and final that you know the formula, every time you have to look it up, write it down again until you don't have to look it up anymore. So the requirements, we have to start in the form ax squared plus bx plus c equals 0, similar to how we solved these quadratics back when we only were looking at ones that were factorable. If we have that format, then automatically we will know x is equal to opposite of whatever b is, so just flip the sign on b, plus or minus square root of b squared minus 4 times a times c, all divided by 2 times a. Again, unfortunately, in this class, you don't get to see where that comes from, but it is a nice, handy tool to have. So we'll start with one that we actually could solve by factoring and see that it does also work with this quadratic formula. So here we're already set to 0, so that's done for us. So I'll just identify a, b, and c. So a is the unwritten 1, b is worth -9, and c is worth 20. So then x is equal to opposite of -9 would be +9. Plus or minus, that's part of our formula. Square root is part of our formula. A little hint for the b squared. Negative times a negative is a positive. Positive times positive is a positive. 0 times 0 is 0. You're never going to have a negative number camped out here since we don't allow non-real coefficients in this course. So -9 times -9 is +81. -4, that one just comes from the formula. That's there every time you use quadratic formula. Times a is 1, times c is 20. And all of that, including this 9, are over 2 times, in this case, 1. Our a is 1. So x is equal to 9 plus or minus square root of, remember we multiply before we add or subtract. So I have an odd number of negatives, this will stay a negative. 4 by 1 by 20 is 80. Downstairs 2 by 1 is 2. So x is 9 plus or minus square root of 1 all over 2. What we do from here depends on this number underneath the square root. 1 is a nice, neat, pretty perfect square, so we can keep going. So x is 9 plus or minus the square root of 1 is 1 all over 2, and then we can break that up. So x is 9 plus 1 all over 2, union that with x is 9 minus 1 all over 2. So x is 10 halves, or x is 8 halves. So x is 5, or x is 4. Both of those are in the set of real numbers, so both of those should be going down here. I ran out of room there. Both of those will go in our solution set. Okay, so our next one, x squared plus 6x plus 9 is worth 0. We're already set equal to 0, so I'll identify our a, b, and c. A is 1, b is 6, c is 9. And x is opposite of 6, -6. Watch your sign work there. Plus or minus square root of b squared. 6 times 6 is 36. -4, that one's always there. Times a is 1, times c is 9. Fraction bar that covers everything, including that -6. So we're 2 by 1. After that, it's all simplifying from there. X is -6 plus or minus square root of odd number of negatives multiplied together. It'll stay a minus. 36 minus 36 all over 2. So x is -6 plus or minus square root of 0 all over 2. 0 also is a nice, neat, pretty perfect square. It's asking what can you multiply 2 copies of to reach 0? Well, 0. 0 times 0 would give us the 0 underneath. So x is -6 plus or minus 0 all over 2. So x is -6 plus 0 all over 2, or x is -6 minus 0 all over 2. But notice both of these turn into the same thing. -6 over +2, so both of them will turn into x is -3. So we only ended up with one solution. Alright, so our next one, we won't have a plain boring coefficient of 1 like last time. We are set to 0. So if we weren't, we had to fix that first, but we are set to 0. So a is 5, b is 11, and c is -12. So x is equal to, don't forget you do need both sides of the equation. X equals is required. Opposite of +11, -11, plus or minus square root of b squared. 11 squared is 121. -4 from the formula times a, which is now 5 instead of that plain boring 1, times c, not just 12, -12, over 2 times, in this case, 5. So x is -11 plus or minus square root of 121. I have an even number of negatives. That will turn this into a plus. And let's see, 4 by 5 is 20. 20 by 12, 240. All over 10. So x is -11 plus or minus a square root of 361 all over 10, and 361 is a nice, neat, pretty perfect square. So x is negative 11 plus or minus 19 all over, pardon me, all over 10. So x is negative 11 plus 19 all over 10, and we'll union that up with x is negative 11 minus 19 all over 10. And we'll just simplify both of those. Ordinarily, in this class, we'd have to throw away the 4/5, but 4/5 is in the set of real numbers, and in chapter 4, we get to keep any real number, so that's going in our solution set, as is the negative 3. Wait a minute. Yeah. Negative 4/5 and negative 3. Both of those will work just fine. Okay, just a couple more of these. X squared plus 3x plus 12 is equal to 0. We're in the right format. Ax squared plus bx plus c is 0, so a is 1, b is 3, and c is 12. So x is equal to opposite of positive 3, negative 3. Plus or minus square root of 3 squared is 9. Minus 4 times 1 times 12. All divided by 2 times 1. So x is negative 3 plus or minus square root of 9. Odd number of negatives, this will say a minus. And 4 by 12, 48, all over 2. So x is negative 3 plus or minus square root of negative, and here's where we're running into trouble, 9 minus 48. Unlike signs, subtract those absolute values, and the negative was further from 0. So let's see, so 18 minus 9 is 9, 3, so negative 39 all over 2. As soon as I see this, square root of a negative, we know that we've been kicked out of the real numbers. So our solution set is empty for that one. All right, so one more. We have a couple steps to it. And there, centered fine there. 2x squared plus x is 2. This time we're not set up in the right format to solve this. We're not set to 0, so I will fix that. I will subtract 2 on both sides, giving us 2x squared plus x minus 2 is equal to 0. So a is 2, b is the unwritten 1, and c is not just 2, but negative 2. Watch your sign work there. So then x is equal to opposite of 1, negative 1. Plus or minus square root, all that comes from the formula. B squared, 1 squared is still 1. Minus 4 from the formula again, times a is 2, times c is negative 2, all over 2 times a is worth 2. So x is negative 1 plus or minus square root of 1. I have 2 negatives multiplied together. This will turn into a plus. And let's see, we have 8 by 2, 16, all over 4. So x is equal to negative 1 plus or minus root 17, all over 4. Now what's making this one a little bit different than the last few that we worked with is 17, not a nice, neat, pretty perfect square. So think back to those square root method ones where we had something that wasn't a nice, neat, pretty perfect square. It stayed under there in our solution set. So we have two answers, negative 1 minus square root of 17 all over 4. Negative 1 plus square root of 17 all over 4 as well. So these are two real number answers. They're not pretty real numbers, but definitely real numbers for our solutions. And those are the only two real numbers that will make that work. All right, so that should give you enough ammo to finish out section 4.3. And again, if we have time at the end, I doubt we will, but if we have time, we'll go back and look at 4.1 and 4.2. But those are mainly rehashing things that we've already done. If you have questions, get in touch with me. Otherwise, I'll see you next time. Stay safe out there.